Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Hi, everyone. I am Dr. Moiya McTier, an astrophysicist, a folklorist, and a good friend to the universe. And I like introducing my friends to my other friends, like
me, Connie.
Yeah.
I am definitely overwhelmed, but also a friend to the universe.
Yes, you are. It's really nice to see.
Bestie, right now I am putting together some social content for our merch. I am so excited getting to see our vision in the crystal clear JPEGs has been really fun. I think I'm newly excited for our enamel pin. My goodness, when you look at it, don't forget to look on the back. And I'm really excited well, not excited because I've been stressed lately. So I'm going to need the stress ball that we have. I'm going to need that asaptually. I think it'll help.
You can still order them. So head on down to the link in the episode description and you can order our merch. I am especially excited for our blanket,
Yes.
which is made of recycled cotton. It's a knitted blanket. It's very cozy and it rolls right into today's topic because we are talking about things in astronomy that start with B, like this blanket, which is space because it's in the universe. Today, we are doing another installment in our Astronomy from A to Z series. We're doing B is for Bastronomy today.
Great. Love it.
Love it. There are a lot of really interesting things in space that start with the letter B. Connie, can you think of any?
That A was easier. B, not Beyonce.
I mean, in the way that we are all space, yes, but that's not what I meant.
No, I'm like, what's at least a constellation, but I can't even think of a constellation. B is hard, bestie. B is hard.
Yes, so for constellations, we have Boötes. We have, I was going to say Berenices, but it's Coma Berenices. For other things, black holes, black body
holes.
Radiation.
Yes.
Brown dwarfs.
The dwarves.
Yes. So those are all things that we are not going to cover in this episode because we've talked about it before on the pod.
Yeah. I was like, B's tough, but there I know some things. Okay.
You know some things, yeah.
And I'm about to learn some more.
Exactly. By the end of this episode, you'll know a lot of B things. We're going to start with B-type stars.
Okay.
It's one of the 7 types of stars on the main sequence, and it's the second hottest type of star.
Oh.
B-type stars are more than 2 times the mass of the sun and less than 16 times the mass of the sun. So they are larger, they are hotter. The sun's temperature is around 6,000 Kelvin. The temperature range for the typical B-type star is between 10,000 and 33,000 Kelvin.
Oh. Whoa.
It's pretty hot and it's very bright. They can be between 25 and 30,000 times the luminosity of the sun. So between 25 and 30,000 times brighter than the sun.
It sounds like if we could even be near that kind of star, it would just, like, the entire planet would just be sun. Like, we wouldn't be able to see. It would just be brightness. That's what it sounds like. Like, you're just opening your doors and it's just...
Yeah, these stars, you typically don't find planets around them, and that's kind of because they don't live long enough to form planets and stable orbits. A typical B-type star will only be able to fuse hydrogen into helium in its core for about 100 million years. And it can take about 50 million years for terrestrial planets like the Earth to form around stars.
Okay.
So, yeah, it would be really hard to imagine what it'd be like to be around this type of star. Some famous members of the B-type star family include Rigel in Orion. He's, if Orion is facing towards us, it's, I guess, technically Orion's left foot. But from our perspective, it is the bottom right star in the Orion asterism.
Okay.
We also have Spica or Spica in Virgo, which is Virgo's left hand, but it's on the right side from our perspective, and Algol. Algol is actually a triple star system in the constellation Perseus, and the biggest, most massive star in the system is a B-type star. And the others are closer to the sun and less massive.
Okay. Are those star names related to the constellation at all?
Good question. I know that Algol is an Arabic name that means the demon star.
Oh. Ooh.
And so it's not, I mean, it could be because Perseus is holding Medusa's head. And so I think Algol is supposed to be one of Medusa's eyes, maybe, but from a different mythology, obviously.
Right.
So these associations get carried from one culture to another often.
That's cool, though. I like that still.
Yeah. Yeah, it is. So that's B-type stars. The next B term that we're going to talk about is Battie's window.
I know you were so excited to put this on the list for me, Bestie. I know you were.
Yes.
Because, listeners, it is spelled B-A-A-D-E. And I was like, okay, bod. Like, bod. Or you would say just bade. Like, for some reason, whatever culture this is from, they would say bade. Like, it would just be something unusual. And I was still not expecting baddie. I was ready for a bunch of scenarios, and that's not the one I expected.
Sometimes the universe just gives us these gifts. Battie's window is named after Walter Battie, who's a German astronomer. He got his PhD in 1919 in Germany, and he's not Jewish. He's long dead. He was not Jewish, but he did leave Germany in 1931, and he took some of his Jewish colleagues and friends with him, like made efforts to get them out of Nazi Germany. So thank you, Walter Battie. And then he started working at the Mount Wilson Observatory in LA in 1931 and was there for more than 2 decades before he moved on to work somewhere else.
Wow.
And then he retired because astronomers will work until they pass.
Yeah. Y'all should work on that.
Well, when you love what you do. So he, in the 1940s, was observing the part of the sky close to that swath of the Milky Way, like the galactic plane. Within the galactic plane, there's something called the zone of avoidance. It covers about 20% of the entire sky, and it's a region along the galactic midplane that just has so much dust between us and the center of the galaxy that it blocks a lot of the light, or it will reflect a lot of the light around the dust clouds, and that makes it hard to tell where the light is coming from. So objects that are closer to us and objects that are really far away, like even extragalactic sources, so distant galaxies or galaxy clusters, they get mixed up so you can't tell what's near and what's far in these clouds of dust. And the only way you can see them at all is not with optical light, but with radio light that can pierce through the dusty parts of space because the wavelengths are just so long that they pass right through the dust.
Space is crazy. Like, science is crazy. Because what do you mean that from this little tiny planet, we have invented some kind of device because we've observed the natural universe, and now we can see through clouds of dust in the Milky Way?
Yeah.
Wow.
That's the crazy part to you? Just telescopes?
A little bit, because I'm just like, wow, from this little planet, we can see all the way over there.
Yeah, it is amazing.
Yeah, I'm still down on the level of telescopes are crazy.
To be fair, that realization is actually what got me hooked on astronomy. The idea that we, from our little pale blue dot here on Earth, could study things billions of light years away. I thought that was so cool.
And so, back in time, you time travel, bestie.
Yes, we do.
Crazy.
The thing is, Walter,
brazy. It's a B episode. Let's go with brazy.
There are some people who would be very proud of you for that.
Yes.
That's brazy, yes. Battie's window actually isn't even that far away. It's a region in the Sagittarius constellation. I have an image for you, Bestie.
Okay.
So if you look at the asterism of Sagittarius, it kind of looks like a paper boat.
Okay, yeah.
Right? A part of it kind of looks like a paper boat. And Battie's window is this little circular region right off the tip of the Sagittarius boat, or the Sagittarius teacup, as it's sometimes called.
A teacup!
Yeah. It was actually a boat. There was a separate boat asterism when the Babylonians put their constellations in the sky, and then that got absorbed into a centaur constellation right next to it and became Sagittarius.
Oh. Huh.
But that was... I digress. Battie's window is right off the tip of this Sagittarius asterism, and it's a little bit south of the galactic center. Everything else around it is dark because it's covered with dust, but there's this really bright circular region. It's about 1 degree in diameter. For reference, the full moon is about half a degree. So this area of the sky is like 2 full moons across.
Okay.
Just a little bit south of the galactic center. And it is the brightest, clearest region towards the galactic center that we can study. And so we can actually see some globular clusters in Battie's window. The most important of them, the most significant of them, is called NGC 6522. And
Great name.
Great name. NGC is the new general catalog. So it's just the catalog of like bright, fuzzy objects in space that we haven't really classified yet.
Okay.
And it includes a lot of nebulae, some galaxies, some galaxy clusters, and globular clusters, which are dense collections of stars that are gravitationally bound to each other within the Milky Way. And a lot of them are probably remnants of old galaxies that were absorbed or accreted into the Milky Way due to gravity, like many billions of years ago. Pretty cool.
Very cool.
So NGC 6522 is in the center of Battie's window. You can also see a couple of bright stars in the Milky Way bulge. You can see some regions of this that are strangely devoid of stars. And that's interesting too, because, you know, we expect space to kind of be like spread out, kind of homogeneously, is the same everywhere. And there are these relative underdensities within our own galaxy. That's interesting.
Yeah, that is interesting. Like, that's where all the black matter's hiding. No, dark energy.
No, but I appreciate you trying.
I tried. Yeah.
So Walter Battie found this in the 1940s, and he was looking at a couple of RR Lyrae variable stars. We can talk about that when we get to R is for astronomy.
Okay,
but
great.
They are a particular type of star that varies in brightness over time, and you can use them to calculate distances to that object. And so he was able to calculate the distance to the Milky Way bulge, to the center of the Milky Way from the Earth, and he estimated it to be about 27,000 light years, which is really close to the value of like between 25 and 26,000 light years. But we will come back to Battie at the end. I have a fun little game plan for us.
Okay.
Because you're right, I was really excited to tell you that. Okay, next up we have the Balmer series, Balmer. Do you remember in our ultraviolet episode when we talked about the Lyman series at all?
I'm gonna say no, but I remember Lyman.
It rings a little bell. Great. So both the Lyman series and the Balmer series, they're a group of spectral emission lines. So if you're looking at a target and photons at like a specific wavelength or a specific energy, they're emitted from that target, you will see a spike in the spectra at that wavelength. So you'll see like an emission peak there. The Balmer series is a group of those types of emission peak lines associated with particular transitions in the hydrogen atom. So a hydrogen atom typically is going to have 1 proton, 1 neutron, and then typically 1 electron on the outside. But that electron can be in multiple energy shells. You know, they can be in like the base energy shell all the way up to like infinity, depending on how much energy it gets. Those electrons will move from one energy shell to another. When the atom absorbs a photon, the electron picks up that energy and it will jump up to a corresponding energy level. But when an electron falls back down to a lower energy, because these particles are lazy, they want to be in the lowest energy state possible.
Same.
That atom will emit a photon that matches the energy difference between the energy shells that the electron jumped between. Does that make sense?
I think so, because I'm remembering when we talked about Lyman, I believe you did explain that things kind of can come out when it drops down. Like that was an interesting
Yes, I mean that is a phenomenon that is really important in all of astronomy. Photons are emitted from atoms when electrons jump down to lower energy levels. And the Balmer series is specifically for transitions from higher energy levels down to the second energy level. So from 5 down to 2, 4 down to 2, or 3 down to 2. And each of those different jumps is associated with a particular amount of energy. So they will release a photon that has that amount of energy. But there are all of these different jumps. So if you are going from level 5 down to level 2, that's a big difference in energy. You are going to release a more energetic photon than in the transition from 4 down to 2. Because that's a smaller energy difference.
Yeah. Okay.
Great.
Bestie, did we also talk about this in the microwave episode?
I mean, we talked about this phenomenon for sure, but not these lines, because the Lyman series is shown in the ultraviolet.
Okay.
Yeah, they are jumping down to the first energy level. So that's a really big jump in energy, which means you're going to get a high energy photon in the ultraviolet. These Balmer series lines, they appear in the visible part, the optical part of the spectrum, because they're jumping down to level 2, which is a smaller energy difference. And so they release smaller energy photons.
Okay. Yeah.
Excellent. You can then kind of imagine that there are other types of emission line series. So if you can have a series, it's actually called the Passion series, not spelled like the emotion, P-A-S-C-H-E-N. The Passion series is for transitions down to the third energy level. If you carry that up, you end up with something called the Bracket series. It also belongs in B is for Bastronomy.
Ooh.
The Bracket series is named for Frederick Bracket, who observed this series for the first time in 1922, and that's transitions down to the fourth energy level.
Okay.
By the time you're there, that's in the infrared part of the spectrum, because it's even lower energy photons being emitted.
Right, because it's not as big a jump.
Exactly.
Okay.
Yes, perfect.
Okay.
The Balmer series was named after Johann Balmer, who came up with this equation to calculate the wavelengths where all of the emission lines in the series should be. He did that in 1885, which is about 2 decades before we started to really understand quantum states, which we talked about last week, and like the discrete quantized packets of energy that are associated with this process. So it's really cool that Balmer was able to mathematically figure out where these transitions should be before we even really understood the fact that these photons are being emitted at specific energy values because of that electron jumping energy levels. Like, I just love that they could figure that out.
That's cool.
Yeah. The next B I want to talk about, I think you'll like this as a photographer, bestie, is called the Barlow lens.
Okay. Who was Barlow?
Peter Barlow was a mathematician and a physicist who did a lot with optics and lenses. He invented the Barlow lens in the 1830s, so that gives you a sense for when he was working.
Yeah, very early days of photography. That's the
very
time.
Early days of photography, yes.
Yeah,
but
overall.
Like, you know, I'd say in medium days of optics.
Right. Yeah.
The Barlow lens is a special device. It's not just a single lens, so this is a kind of confusing name, but it's a device that usually involves multiple lenses in a specific order at specific distances from each other in a tube, and the device is used to magnify images seen through a telescope or a camera.
Oh, to magnify.
The way it works is that you have this series of convex lenses, and they are arranged precisely to collect all of the light that's collected by the telescope before it gets to the eyepiece. So it collects all of the light, and then it refocuses that light at a greater distance, which essentially, effectively, increases the focal length of the telescope. When you can do that, but you keep the focal length of the eyepiece the same, that ratio of the two focal lengths is how you get the magnification of your image. So if you keep the eyepiece focal length the same, but increase the telescope focal length, you end up with greater magnification. The issue, though, is that with increased focal length for your telescope or your camera comes a decreased field of view. It's almost like squinting your eyes. Where when you squint your eyes, your field of view is smaller, but you can better focus on the object. So the Barlow lens is kind of like helping the telescope squint.
Yeah. It reminds me of a telephoto lens, honestly, because when I have a zoom lens, you can have a fixed lens or a zoom lens. And that could be a varied length. And so in my regular zoom lens, I have just like a standard DSLR, and it comes often with get an extra lens for zoom. I forget what it goes to, but you have to like turn the actual lens in order to change the focal length in the lens. And then when you're looking farther away, you can still kind of focus and tweak and stuff, but I do understand it because I'm like, oh yeah, if I'm looking across a bay at a bridge and I'm looking in a zoom lens, it is like I get much less of the bridge. I can't see the whole thing because it's letting me focus on just that part. And I do believe that is a better magnification than like the digital way that we do it. It reminds me of that difference of like using just like a point and shoot that can't change its lens, but you can still like zoom in like on your phone. But on an actual camera, that's why they're better, because they're actually like doing the optics stuff that we learned about all the way back here.
Yes, they're actually doing the optic stuff, which changes the way the picture is taken, as opposed to our cameras, which are just zooming in on those particular pixels in the image.
Yeah.
So there's really not even an advantage to zooming in before you take the photo, because you could just do it after you take the photo to have the same effect. Zooming in before you take the photo just helps you, the taker of the picture, see it better.
Yeah, it kind of cuts the process that you would need to do in order to get that same photo from a actual cropped picture, because if you try to like make it bigger, it is gonna just like mess it up. It makes it all like blurry and bad quality.
Yeah, you lose a lot of quality.
Yeah, you'd have to like render it differently, and that's why cameras are still the best.
That's why film
and
cameras,
and good stuff.
Good stuff. You know what else is good stuff?
What?
Weird, obscure, niche units in science. I love them.
We do love those. We do actually love those.
So please let me introduce you to the barn.
No.
Yes.
Bestie, what do you mean? Why?
Yes.
Is it named after a person or something? Like,
nope.
Why a barn? A barn is
I'll tell you.
Dang
I'm
it.
gonna tell you.
Oh, a barn is actually big, but that's only to me. It may not matter, but I'm just like, right, perspective. So, okay, go ahead.
A barn is a tiny unit of area. It is 10 to the minus 28th power. All right, so a decimal point, 27 zeros, and then a 1.
Wow.
Square meters. It was originally used to describe the cross-sectional area of atomic nuclei, so that one barn equals the cross-sectional area of a uranium nucleus. When I say cross-sectional area, do you know what that means?
It only makes me think it's like three-dimensional, but I don't think that is that simple.
It has to do with the dimensions. I mean, it is a consequence of space being three-dimensional. The cross-sectional area is what you would measure if you sliced an object in half and you were staring at that sliced bit and you measured like the two-dimensional area of that sliced bit.
Okay. In order to get the whole picture?
It's just a measure of size. Okay. An object with a larger cross-sectional area is going to have a larger radius It's a way of taking the 3D volume and representing it in a 2D value.
Okay.
The term was then adopted by astronomers to describe interactions between fundamental particles, like when they hit each other, bounce off each other, scatter each other. All of that is happening on very small scales, still bigger than the quantum scale, but small enough that we need these special units. And the term itself was invented by two physicists in 1942 at the University of Chicago. Their names were H.G. Holloway and C.P. Parker.
Okay, so not their
names.
names.
Not a barn in sight.
No.
In fact, as far as the internet has been able to tell me, the name possibly comes because one of them, I don't know which, one of them was a rural boy, was a sweet little country boy, and was like, this is a quote.
A quote?
That they were talking about this unit, and they're like, it is, quote, really as big as a barn, which I don't totally understand. I think they meant to say that they by having this unit, they were able to now describe a larger parameter space at this micro scale. So it made us better able to see and understand that scale of the world. So it made that scale as visible as a barn. I don't know. But maybe it's also about the perspective thing. I don't know. Either way, we have this unit and it's very fun.
It is very fun.
Some controversy. In 1976, the Council of Ministers of the Electronic Engine Controls.
Sure.
I guess they decide standards of units in engineering. They tried to abolish the unit. They tried to get people to not use this unit.
They're like, this is ridiculous. I hate this. Someone stop this.
Instead, they wanted to switch it over to be equivalent to 100 femtometers squared, which is worse. I would much rather talk about a barn.
Yeah.
And so the abolishment was not successful, and people still use the barn.
You got to come up with a better marketing strategy. People's marketing strategy is just not good because that's not a good replacement name. That's not a good replacement name for the barn. It's too much of a mouthful. If this is supposed to be a unit of measurement, it should not be several syllables long. Not that many.
Actually was part of the discussion because originally they wanted to name it after some scientists. They ran into a bunch of different issues, one of which was that a lot of the scientists' names were too long to be a unit.
Yeah, it was like the Baker Way.
They honestly didn't even consider naming it after themselves. That was not...
but in the rename, I would have went back to that. In the rename council, I would have been like, okay, let's see if we can come up with something from their names, and then it represents them, but they didn't have me there.
I actually hate eponymous units.
Yeah?
Eponymous units are okay. I think eponymous phenomena are stupid. I think that the names for phenomena and objects should be descriptive and not named after people.
Yeah.
Speaking of eponymous objects, we have Barnard's star coming up next. Barnard's star is the fourth closest star to the sun after the Alpha Centauri triple star system. So, if you count that the Alpha Centauri system as one, then Barnard's star is right after it. It is only 6 light years away, so it's really close. And it was technically discovered, a human being looked at it and saw it as significant for the first time in 1916. That was Edward Barnard, not the Barnard who founded Barnard College. I checked.
Okay.
And confusingly, I think it was something like Frederick Barnard who founded the college. His father is named Edward Barnard, but it's not this Edward Barnard.
Oh. Okay. And he's like, I want to open a school for women.
He was a Columbia professor, and so he opened the Barnard School for Women. And so that's just, fun little naming tidbit of information. Edward Barnard discovered this star, even though it had been photographed on Harvard's photographic plates in the 1880s. But Barnard came along and he saw this star and he measured its proper motion. Proper motion is the amount of movement that a star seems to have across the sky. And I think we've talked about fixed versus wandering stars before, right? The wandering stars are actually the planets because they seem to move very fast compared to the fixed stars behind them, which all seem to move as one. They move across the sky over the course of the year, clear, but that's just because the Earth is going around the sun.
Right, yeah.
They seem to have the same bulk motion for the most part.
Right.
But some stars, because they're closer to us or because of the nature of their orbits, they have a larger proper motion. So they seem to be moving even compared to the fixed stars.
Yeah, okay.
Although, to the Babylonians, they would have been one of the fixed stars. But Barnard's star is really dim. It's an M-type star that's only about 20% the size of the sun, only about 16% its mass, and it's older than the sun. So it's notoriously difficult to constrain the ages of stars with precision. A lot
They're
of
like,
the methods...
I will not be constrained. Do not ask a lady her age.
Exactly. It's rude. It's rude. And they're going to keep that mystery as long as they can.
Yeah.
And so a lot of these methods we have for determining the ages of stars, they have error bars, like up to 200%. And so our best constraints for the age of Barnard's star is between 7 and 12 billion years. We just know it's old. Old enough that it seems to have quieted down a lot. It doesn't spin as quickly. It takes about 130 days to do one rotation, and it's not as magnetically active.
Because she's old. She's chill.
She's chill. She's chilled out. But she's, in the grand scheme of her lifespan, very young. She will live over 1 trillion years.
Oh my goodness.
And it's moving very fast. Its proper motion is 10 arc seconds per year. So let's take a degree. We have 1 degree on the sky is made up of 60 arc minutes.
Okay.
Within each arc minute, there are 60 arc seconds. So it's like 1/3600th of a degree. And Barnard's star is moving 10 of those every year, which doesn't sound like a lot because I just described how small an arc second is, but the typical proper motion for a star is only 0.1 arc seconds per year.
Yeah.
So this is 100 times faster.
Wow.
And if you translate that proper motion into an actual velocity of the star moving through the Milky Way galaxy, it's moving at about 70 miles per second.
Whoa.
Towards us. Kind of. Not like directly towards us, but it is coming closer. And so now it's about 6 light years away, but over the next couple thousand years, it's going to come within, I think, closer than 4, like something like 3.75 light years away from us.
She'll be coming around the mountain when she comes. She'll be coming around the mountain when she comes. I'm like, oh boy, that's she's on her way. I'm on my way.
She is. Yes, bestie. And she's not alone. She is carrying with her 4 planets, as far as we can tell. These planets were discovered in 2024, and they are all closer to the star than the habitable zone would be, so they're probably very hot. The longest period of one of these planets is 7 days to go around its star, and all of them are less than 35% the mass of the Earth. So they are small, rocky planets that orbit very close to their star. I would be shocked if any of them have an atmosphere, but we haven't been able to determine that yet. And that's Barnard's star. Huh. It, I think, was named officially Barnard's star in 2016, 2017, and I think it may have been one of the last objects to be named after like an astronomer person, because they kind of changed the nomenclature rules after that.
As they should.
Hey friends, it's me. Connie and I got an urgent craving for boba and baklava, so she went to get us some from the Podiversity food hall, and I'm going to take these few minutes while she's gone to share some messages with you. The first message is a big thank you to all the patrons who support the show every single month. We're an independent podcast, so we rely on support from listeners like you, so thank you so much. And we want to give a special shout out to our sun-like stars, Scott Reynolds, Tom T, Seven Petrichor, Ashley Shambo, Bruce Sedloff, and Kelly Bennell. Thank you. You're golden. You're perfect. And we appreciate your support so, so much. If you want to join this stellar group of people, you can hear your name on the show, make it onto our patron star chart, and get access to research notes for most episodes. All of that for $5 a month at patreon.com/palebluepod. You can also make a one-time donation and become a supernova in the Pale Blue Pod sky. That's at the PayPal link in the episode description. And if you can't support us financially at all right now, we understand. The best way to help the show grow is to rate and review us on whatever podcast platform you use, and to share a specific episode with a specific person who you think would enjoy it. But no matter what you do, if you do anything at all, thank you for listening to the pod. Connie and I are honored to be a part of your week. My next message is a podcast recommendation. It's another show in the Multitude Collective, and it's called Simple and Clean. Have you ever heard of Kingdom Hearts? It's a video game that follows the story of a lost boy trying desperately to find his two best friends with the help of Disney's Donald Duck and Goofy, while defeating strange little monster guys called the Heartless across a series of Disney movies. Does that sound cool to you? Or maybe just like really wild? Either way, you should check out Simple and Clean, a show all about video games, Disney films, and the weird place that fandom occupies in between. Follow hosts Mayana and Misha as they navigate a game series many people love, and even more people couldn't even begin to understand why it's like that. If you've never heard of Kingdom Hearts, that's okay. They're here to break it down for you and explain why they love it, and hopefully convince you that this weird little story deserves a place in your heart. Don't worry, they'll keep it all simple and clean. New episodes come out every Sunday. Connie is back. We're going to take a little snack break and then get back to the Bastronomy chat. The next B is baryon.
Baryonic chambers? Is that? No, those aren't related. Are they related?
Perhaps. Baryon is a general term for a type of particle. And so if you see the next one after this is going to be the baryonic acoustic oscillation, baryonic matter. I imagine a baryonic chamber in a type of accelerator or something.
Hyperbaric?
That does make more sense in a medical context.
Yeah.
Or like a general life context.
Yeah.
Because technically all chambers are baryonic, because all chambers are made of baryons. Here's the thing, y'all. When we talk about matter in the universe, there are two types of matter. There's dark matter and there's baryonic matter.
Oh.
So baryons are particles like neutrons and protons that are made up of odd numbers of quarks. I know I've talked about quarks many times on the pod. There are 6 types of quarks. They are fundamental particles, so you, as far as we know, cannot break them into smaller pieces.
Okay.
And you need to combine them to make up other small particles like protons and neutrons. They are each made of 3 quarks. You can have other types of particles that are made of quarks, but even numbers of quarks like the meson, and that is not a baryon because it has an even number of quarks.
Okay, so baryons are odd and mesons are even? Or no, it's just 2. Not even, but
correct. Yeah, because
those
baryon is
2.
the umbrella term. A meson is a specific type of particle that is made up of 2 quarks. Mesons are separate from baryons. Baryon is an umbrella class. Within baryons, there are protons and neutrons and other types of particles. But we are most familiar with protons and neutrons.
Okay.
In the kind of Russian nesting doll that is particle physics classification.
That might actually help me if I look into it more like that.
Yeah, I mean, it's a Venn diagram. I have an image for you in the notes that splits it up. Particle physicists love to split things up into their little classes. So we have a complicated Venn diagram where we have hadrons, which are any types of particles made up of quarks. Within hadrons, we have that odd even number split. Right?
Okay.
So we have baryons with the odd numbers. So baryons are types of hadrons. All baryons are hadrons.
Yeah,
Not
it's
all
getting real
hadrons are
SAT up
baryons.
here and here.
Yes, it is. Baryons are also a type of fermion. This is another class of particle physics. Fermions have... Remember when we talked about quantum spin in the quantum episode? There's like this like at the fundamental level, particles can have like full spins or half spins. They can have a spin of 2 or 2.5. Okay. If they have a spin value that has a half in it, it's a fermion. That's not. I don't think anyone in their daily life needs that information, but for the people who really want to understand these classification schemes, there you go. So a baryon is just a type of particle that is made up of 3 quarks, and all of the matter that we can see is made up of baryons and other types of particles.
Not to say that I pay all that attention, but I was like, I've never heard of Barry. Who's baryon? I don't know him. And it's all the
Sorry
the
to that
particles.
man.
Yeah, sorry to that man.
Yeah, so when I am talking about dark matter, I will often differentiate it from, I'll call it baryonic matter or visible matter or luminous matter or like non-transparent matter. But it all just means stuff made of quarks and because they are made of quarks, they interact with all of the 4 forces.
Right.
As opposed to dark matter, which is not made up of quarks because it does not interact with any of the forces besides gravity. So remember when we were talking about quantum field theory and how the fields can couple or interact with each other? Whatever dark matter is made of, whatever its particle is, its quantum field, assuming this is the correct theory, the dark matter particle's quantum field does not interact with the photon field or any of the other force fields, except for gravity.
Okay, because I was thinking about the wildflower field metaphor, and I was like, would dark matter be the air between? But I think not.
I mean,
still,
we talked about there being the grass field and the air field and the water field below. I mean, these are just 3. We would really need over a dozen fields to properly explain it. So. Yeah, it's just a different type of field.
Okay.
Great. So now that we've covered baryons, we can cover the baryonic acoustic oscillations.
And I'm like, yeah, I got to give it to you. Those are 2 different things. I'm like, listen, you use baryon twice, but as different letters, but completely different thing.
Well, the reason I included baryon first was so that you would understand what baryonic means.
Okay.
Baryonic just
Thank you for
means
that.
that this is a phenomenon that happens to baryons.
Okay.
The baryonic acoustic oscillations are this large-scale pattern that you can see in the matter distribution of the universe. If you zoom out enough, you can almost see that like a sound wave moved through the universe and collected matter at the peaks, and then there's less matter in the troughs of those like sound waves of that pressure wave that moved through the universe. So what this pressure wave would have happened very early on. I'm talking before atoms formed, and that happened at about 400,000 years after the Big Bang. So earlier than that, before there were atoms, when there were just like quarks and like maybe some of them had formed into protons. I'm not sure. Over time they did, like definitely. But at the beginning, it was just a bunch of fundamental particles moving around. And the universe had inflated already. So it was bigger than it was for like the actual Big Bang. But it still had to expand a little bit. And dark energy, we think, might not have been as strong, so gravity could still kind of hold its own. And what was happening was that the universe was trying to expand, but gravity was still pulling the material, all of the baryonic material, together. And when it did that, the material was packed tight together and it got hot. And all of that heat created an outward pressure that pushed the material away from each other. That gave it more space to cool down, and then gravity could be like, oh, I'm going to get you back again. Come towards me. Everything gathered together.
Gather.
Yes.
To me, my X-Men.
And that process happened over and over again, it expanding and then gravity calling it back. So this oscillation was happening early on in the universe, and that created a type of pressure wave that got carried through the rest of the universe, and then as the universe expanded, is still visible.
Wow.
So we can actually see, I have pictures for you, Bestie. This
see.
top picture is more of like a simulation where you can see, it starts with like the cosmic microwave background, which shows us how material was distributed at about like 400,000 years after the Big Bang, like at very early in the universe. And then you can see the idea of those circular ripples moving out from material as the universe expands.
Yeah.
That's kind of a simulation. But if you look at the image below that, I can't remember what large structure survey this is from, but when you see Sloan Digital Sky Survey maps or other maps that have looked at how galaxy clusters are distributed throughout the entire universe, you can still see these bubbles of overdensity, and then in the middle of those bubbles, it's less dense, like there's less stuff.
I see that. Wow. It's also very pretty how they've illustrated this here.
It is. Yeah, I love pictures of the cosmic web. And the filaments of the cosmic web, they are the peaks of this baryonic acoustic oscillation wave passing through the universe.
Wow.
This was first detected in 2005 by two separate teams working on their own. One was working with the Sloan Digital Sky Survey data, and the other was working with 2DF Galaxy Redshift Survey data. We're going to do an episode on the Sloan Digital Sky Survey because it's really interesting, and on that episode, I will probably talk about other large-scale surveys like the 2DF one. Both of these surveys were aiming to map the large-scale structure of the universe. So how are all of these galaxies and galaxy clusters actually distributed throughout space? And when those two different teams measured out how much space is between these peaks of density in the material, it's about 150 million parsecs. Parsec is a special type of unit. We'll talk about it in P is for Bastronomy.
And Bastronomy.
But it is about 500 million light years. So that's the wavelength between these peaks of these waves.
Wow.
And that is actually such a reliable number that we can use the baryonic acoustic oscillation waves as something called a standard candle, which lets us measure distances fairly accurately. But this only works for super long distances, obviously. So it's useful in cosmology when we're trying to figure out what happened early on in the universe. And it's really helpful for studying dark energy, because to understand how dark energy works, we need to study the very early universe, like objects really far away, but we need to know how far away they are so we can identify them as
Fair.
like, yeah, that's actually an early universe galaxy.
Yeah, that's fair.
And so a lot of astronomy is figuring out how far away is that object.
Yeah. Yeah, that is a lot of it. Yeah.
And so this is really important for that. Thank you to the BAO. I'm going to talk about black dwarfs next.
Okay.
I did not come up with this term. I do not necessarily condone this term.
Yeah.
But so it's the hypothetical end stage for a white dwarf star. So like once we had the white dwarf term, which also not great.
Yeah.
Not great. Once we had that term, black dwarf was kind of just like the next logical language step.
Yeah, there's red, there's the other ones. So like, okay, sure.
Well, white because it's glowing, black because it's not. So the idea of a black dwarf is that it is the end stage of a white dwarf after it has radiated away all of its energy and it doesn't glow anymore. We've never seen this stage. It's completely hypothetical because that would take just so long to happen. The exact timing depends on some tricky details about how different atoms or different particles will decay into other particles and how dark matter behaves. But estimates say that at the low end, it would take 10 to the 15 years. That's a quadrillion years for one of these black dwarfs to form. But it could be longer because other processes can happen inside to like kickstart fusion or make it glow a little bit. And it could take as long as 10 to the 37th power years.
No, that's too big. That number is no.
It's quite large. I will blow your mind even more. After the black dwarf forms and it's not glowing, it's not fusing, because of spontaneous processes at the atomic and like quantum level, it is possible that a black dwarf could go supernova. After about 10 to the 1100th power
Don't do this to me, bestie.
years. After that, huge amount of time, a particular nickel isotope could potentially decay into an iron atom. And that would happen because of the weak nuclear force, which can turn down quarks into up quarks and like change the fundamental nature of atoms. So the weak nuclear force could create this iron atom, which would trigger a chain reaction of runaway nuclear fusion. And if you have a particular mass of material, that could create a supernova explosion, like way, 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 way out. I think 10 to the 1100th power years is definitely after... like it's definitely
Everything?
after M-type stars. No, not everything. I think we did a long-term Fate of the Universe episode. Yeah, where we talked about all of the weird kind of quantum processes that can happen.
We did, but I still can't wrap my head around it because I'm just like, okay, so the star is no longer glowing, but there's still the stuff in it. And so it could like react. We just don't know how it will react, but it could react enough to trigger, wait, you said runaway nuclear fusion?
Mm-hmm. And it's not even like react. It's not a chemical reaction that's happening. It is a quantum fluctuation that spontaneously turns one, or actually it could also be like it could either be a quantum fluctuation that spontaneously changes stuff, or it could be a matter of protons decaying into other types of particles, which, can also do something.
Wow.
Yeah. Let's talk about the Boltzmann constant.
Okay.
Ludwig Boltzmann was, I think he was Austrian, maybe.
Okay.
He was a scientist who was active during like the birth of thermodynamics as a field, and he was studying the relationship between energy and temperature. But he did a lot of conceptual work, and then other people came along and did the math to figure it out. But they've still very nicely named things after him. So the Boltzmann constant is a value that was discovered by Max Planck, but the concept of it was thought of by Ludwig Boltzmann. And it just relates energy to temperature. It's used in black body radiation calculations. We talked about that before. It's used in entropy calculations. And here on Earth in engineering, it's used in calculating the thermal noise in resistors in electronics. I thought of that. I was really excited to talk about the Boltzmann constant. And then I got kind of embarrassed because I realized I was actually excited to talk about the Stefan Boltzmann constant, which is slightly different.
That's a different guy?
Well, it's the same guy, different constant. It's just like a different aspect, a different piece of the thermodynamics puzzle that he was working on.
Oh, is this like a hyphenated thing?
Oh, yes. It's Josef Stefan did the math of the concept that Ludwig Boltzmann thought of, and so they named this constant after the both of them.
Okay, so he has two.
He has two constants, yes.
Wow.
And in astro, the Stefan Boltzmann constant is used a lot when you're trying to figure out how bright or how hot a star is, because it relates the shining output power of an object to its temperature. And one of the equations that I used so often in school was that the luminosity of a star or of any object is the surface area of that object, so 4 times pi times the radius squared of that object, times the Stefan Boltzmann constant times the temperature to the 4th power.
And I'm like, okay, is that PEMDAS? Okay, how do I'm like, whoa, that's so many things.
It's all just
together.
Multiplication.
It's a
all
lot
just
of multiplication.
That's just 5 terms. And
But aren't there several equations within each one?
No, this is just one equation.
Oh, okay, because I thought you said you then had to multiply it by the Boltzmann. I was like, whoa, is there another theory you have to multiply by?
One of the terms is the constant. A constant in science is a value that you can just plug into the equation. And the value for the Stefan Boltzmann constant is about 5.67 times 10 to the negative 5th power, so it's a very small number.
Okay.
And that's because it's based on very small units of centimeters and seconds. And an erg is a special value of energy that we only use in astronomy. It's a pretty small value. So yes.
That one I kind of like an erg.
It is nice. Yeah. And so I just wanted to talk about the Stefan Boltzmann constant, and I needed to share.
No, you were supposed to save that for S's for astronomy.
But I didn't. I thought it was called the Boltzmann constant. Therein lies my humiliation. I'm going to move on.
It's okay, bestie. I'll allow it, of course.
You're so generous. Thank you. Next, we're going to talk about Bremsstrahlung radiation, which is also called breaking radiation. This is another broad category for types of electromagnetic radiation, so light, that is produced by the acceleration or the deceleration of a charged particle when it's deflected by another charged particle. Typically, this is for an electron that is being diverted or like turned or curved in its path by a proton or an atomic nucleus that has a positive charge. It's called breaking radiation because it's like the radiation that's produced when the electron puts on the brakes because it's going around like a steep curve.
Okay. All right.
It's a common type of radiation to see in galaxy clusters where you have really hot gas that can ionize, so the electrons can separate from the atoms, so you get these free-flowing electrons, and then you have a bunch of positively charged atoms in a space. So if you have a lot of hot gas, the electrons will get deflected by proton clouds and produce high-energy photons, so we see them in the X-ray often. Oh, and then finally, we have the bullet cluster.
Okay,
are you ready to
I'm
talk about
intrigued.
dark matter a little bit more?
Yeah.
Okay, great.
I can, let's do it. Let's just go do it. Let's do it.
Let's do it. I love the enthusiasm. So one of the biggest pieces of evidence for dark matter, this is after people came to a consensus that it was real, but they still needed some additional proof, comes to us in the form of the bullet cluster. It was discovered in 1992 in a survey of galaxy clusters, but then it was revisited over a decade later by the Chandra X-ray Observatory, which is up in space because it needs to be above the atmosphere to collect those X-ray photons.
Okay.
The Chandra telescope imaged the hot gas in this interacting galaxy cluster. There are two galaxies that are interacting through gravity. One of them passed through the other, and Chandra was able to see how the gas in this merging space is distributed. And then other telescopes were able to detect that there was gravitational lensing happening on either side of the clumps of gas. Each clump of gas is a galaxy. And on the outside of those clumps of gas that have just passed through each other, you see, well, you don't see, but there is a lot of mass, there's a lot of material there because the galaxies behind it are being gravitationally lensed. So the light from them is being bent towards our telescopes so that they look brighter than they would if there wasn't a massive object between us.
Whoa.
So we couldn't see any massive object there, but we could see evidence of gravitational lensing. So people were like, oh, there must be dark matter there. We agree that dark matter is a thing. Here it is in action. So if you look at this image that I've provided for you of the bullet cluster, the pink is the hot gas.
Okay.
There's a clump of hot gas on the left and a clump of hot gas on the right. On the right, it's more of a triangle shape, right? It's a triangle pointing towards the right. That is because that clump has passed through the clump on the left, and just by the pressure of passing through the space, the gas material has streamed out. It's what's called a bow shock, like when the bow of a boat is passing through the water, and then the water creates like a triangular wake around the boat.
Yeah. Okay.
Okay, great. So we can clearly see evidence of interaction between the gas in these two galaxies, right?
Wow.
And then with extra data, we can tell that there is dark matter on either sides of these galaxies. And that's a little bit confusing. Like, why is there such clear separation? Why is the dark matter so separate from the baryonic matter, the gas in these galaxies? This is a really interesting picture because it tells us more about the nature of dark matter. What happened here is that the galaxy on the right passed through the galaxy on the left, and all of the gas interacted with each other. It interacted gravitationally, but it also had some self-interactions. So through electromagnetism, like through the charges, the electric charges, the gas interacted with each other, and also probably through like the nuclear forces, the gas interacted with each other and slowed down a lot. But the dark matter kind of shot past the galaxy on the right as if it was less affected by this galaxy merger. It was able to just pass through everything. So that tells us that the dark matter was only slowed by the gravity interactions, but gravity is the weakest of the fundamental forces. So if it was only slowed by gravity and not slowed by the other stronger forces, it wasn't slowed down as much. So the dark matter kind of raced ahead of this galaxy, and you end up with dark matter on the outside of this interaction and all of the gas on the inside.
Wow.
And so this helped us constrain the force behavior of dark matter and tell us dark matter does interact with the gravitational force, but it does not interact with electromagnetism because those electric charge interactions didn't slow it down. And it most likely doesn't interact with the strong nuclear force because that didn't slow it down. And we're still a little unclear on whether it interacts with the weak nuclear force or not.
Gotta learn that. Someone out there is investigating as we speak.
Indeed. I think signs point to no, but there's still some debate about it. And we are still actively studying this region of space. Recently, like in the last 2 years, JWST has mapped the mass distribution of the bullet cluster. So trying to figure out not just where is the baryonic material, not just where is the gas and stars, but where is all of the matter and how is it spread apart.
There's a lot of stuff going on up there, bestie.
There's a lot of bees in space.
A lot of bees in
the space trap. There's so many bees in the space trap.
Thank you for that, bestie.
You're welcome.
The bullet cluster is like a trap, it seems like. That's
yes,
the bee
but
in the
only
trap.
for the gas.
Just for
only
the gas.
For the gas, not for the dark matter.
Yeah.
I know I threw a lot at you this episode, bestie. Thank you for sitting through it. I do have a little brain palette cleanser for you if you would like one.
Okay, yes, thank you, please.
Excellent. I have a game that I'm calling Baddie or Barn.
Okay. All right.
I have for you a list of B-list celebrities. According to an AOL.com article from 2024.
Love it. Love it. Because you know what? Pop culture also loves to categorize things.
Exactly. And so I have that list actually only gave me actors, and then I came up with people outside of the film industry that I would love to get your thoughts on. I'm going to tell you the name. You just, real simple, have to tell me, are they a baddie or are they a barn?
Okay, so obviously baddie is a baddie, and a barn is just like I'm not that interested.
Exactly, yeah.
Okay.
It's like a tiny unit.
Okay.
But sometimes a barn is really interesting, and good,
absolutely,
you know?
Absolutely. Okay. And then it would be subjective. So we would love to hear what your reactions are in the comments because we may have different feelings about this.
Exactly.
Yeah.
I didn't run this list by you, so I hope you know who everyone is. We're starting off with Jason Momoa. Is he a baddie or a barn?
You know, I think I'm like trying to get to like astronomical in it and like philosophical, but I'm like, I think most people think he's a baddie, but he might be a barn. I don't know. Yeah.
You got the triple gasp.
Yeah. Classic. But he is a barn for me, I think. But
that's fair.
I enjoy his work. I've seen a few things that he's been in, but I'm not like obsessed or like, oh my gosh, I love Jason Momoa.
That's fair. That's fair. Jason Momoa made Stargate Atlantis worth it for me.
Understood.
In the first season, in the first 2 seasons. So for me, he has to be a baddie.
Oh, I understand because you put me and my boyfriend on to C, and my boyfriend was obsessed with it, and I was like, "Nah, Jason Momoa, he's good. I think he gets I don't know if it's typecast a lot, but yeah, I think that's part of the thing. It's like, I want to see something different from him at some point.
You know what? That's a great point. I would love to see him go the way of like Vin Diesel or some of like Dave Bautista's softer roles, you know, where he can show us that he contains multitudes.
Yeah.
Okay. Next up, we have Don Cheadle. Is he a baddie or a barn?
Okay, so he is a barn, but like a good barn in that he is like just a solid little unit that like whatever he's in, he good. He does his job and goes home, I assume. I have not heard anything about him. So I think he's just like a solid, you know, recurring unit.
Yeah. Yeah, I like that. I would recognize him on the street, but I wouldn't like get excited.
Exactly. It's like, oh, is that Don Cheadle?
Precisely. That would be my reaction. So he is a barn.
Okay.
Okay. Next up, Elizabeth Olsen.
This is interesting just because of like her whole family history too. Like her sisters were baddies. Like they were such baddies that it's like she's kind of a barn, but like that's fine. Like I think she's on the farm, just like, you know, bringing in the dough and, you know, I don't know. But I think she's a barn.
Okay.
I do.
Yeah.
I do.
I think she could give baddie if I knew her better.
Yeah.
It's tricky. She's halfway between, but I will agree with barn.
Yeah, it's the sister thing, and I think I watched some YouTube about the Olsen twins semi-recently, and I was like, yeah, because of her sister's experience with fame, I think she just approaches it probably very differently, and so she's probably choosing to be a barn as well.
Good point. Yes. Okay, the final actor, Zoe Saldana.
Okay, I'm gonna put her as baddie.
What?
But not
okay.
But like in a super like a dangerous space way. Like she's very present and visible, but I wouldn't say that that's the best thing. Yeah. So I'm gonna go that way.
I was curious to see what you would do with that. I think like to me, I gotta put barn.
Yeah, no, absolutely. I'm going on like a mind bending, like, oh, if you really read it this way, like it's like, oh, she's gonna like explode, like, you know, at some point. But yeah, she's definitely barn energy.
Okay, good.
Yeah.
Now we're leaving actors and going to writers. I have one writer for you.
Okay.
Sarah J. Maas. Is she a baddie or a barn?
Of all of the writers that you could choose.
I racked my brain for B-list writers, okay? Like I was really trying.
Oh boy, I guess that is B-list. I'm gonna go with barn because you could find her stuff in a barn. Could fill a barn. Yeah.
Fill a barn. I am torn. Unfortunately, I say with a slight amount of shame. A Court of Thorns and Roses series did get me through depression in grad school. Heavy.
You know what?
Like it was helpful.
A barn is a place that is host to feeding and giving life, you know? So like I understand like barn is not necessarily bad, but some barns are better than others.
Some barns are better than and you know some barns have like a part of them, like the loft, that you want to spend all your time in, but you don't want to go anywhere near the bottom part of the barn.
Exactly.
You know?
Like there's a particular place you feel good at, and then the rest of it is kind of like not that well taken care of, but like you found your spot that you can deal with. You know, you've made it your own, you've made it your home, and that's it.
Yeah. I have a nostalgic place in my heart for A Court of Thorns and Roses. I DNF'd the second or third book in the Crescent City series, and I recognize that she has a lot of problematic shit going on. And so for that, she is a barn.
I think I did. I don't even remember which series I opened and tried to start, and I made it maybe 5 pages, and I was like, no, I can't do it. And I might have been listening to the audiobook, and I still was like, no.
Is
there a character with an F name?
Yes, Feyre.
Yeah, that might have been the one I started.
Yeah,
I was like,
that was A Court of Thorns and Roses.
Yeah, I'm like, I not for me. But I love a trashy romance, so I could still get to it, but, for free. Because I'm not going to pay for that.
Correct. If you're going to read any of them, read the second one. That's all you need.
Okay, sure.
Yeah.
Maybe I'll give it a try. But I need to catch up on Fourth Wing, so.
You have priorities.
Yeah.
We are now moving to the realm of athletes.
Okay.
Please tell me, is Naomi Osaka a baddie or a barn?
This is like last week's episode where you were like, bring 5 celebrities or famous people or fictional characters. And I was just like scrolling Twitter and I was like, oh, these are the names that I came up with. And I feel like you must have been scrolling TikTok. Like, oh, John Cheadle's in something. Cool. He's one.
Oh, no, that was from the AOL list.
Oh, yeah, the AOL list.
But Naomi Osaka is because I just saw a video about like breaking down her fashion choices.
And that is why she's a baddie. She
100%.
is the pillars of creation. She is something, she is just so, like, okay, maybe not that far, but like something really pretty in space, and that's the first thing I thought of. Okay?
I love that.
But I love the energy she's bringing to tennis with her fashion, like specifically. I don't really follow tennis that much, and I'm like, go black girl, go. But I'm really here for the fits. Like, I'm like, ooh, that's cute. Like, can someone sell that? Like, I might wear that cute little tennis skirt. I love the like flair that she's giving to it, because everywhere could have some whimsy, and they are really being annoying about her whimsy. And so I'm like advocating for it even more.
They are. And it's whimsy, but it's also like deep respect and education. Like, she is clearly paying homage to historical moments and people and trends. Like, it's art.
Yeah, very Zendaya and La Roche too. And how it's like, makes a statement in the way that clothes becomes fashion.
Could not agree more. Baddie, 100%.
100%.
Listeners, you are all also baddies. And that is because you are space. Don't forget that.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram, or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.